Okay. Morning. Um, so I'm not going to be in today or tomorrow. So I'm going to do both of these classes with videos. So you need to listen to these because I'm not going back over this. So it is important that you can listen to this and understand it. Mr. O'Rourke was saying he started this yesterday, so hopefully that went okay. It's a really, really important formula, this Newton's law of universal gravitation. So it's a law basically that governs the gravitational force between two objects, and kind of tells you what that force depends on. Okay, so just to briefly go over this, just because I'm going to do, he said he left you problem 10, was it? Oh yeah. So the force is dependent on, so the first thing here is the product or multiplication of the masses. Okay, so the force of attraction between two objects is dependent on their mass. Now, force is actually a very, very small, the gravitational force is, in the grand scheme of things, a very small force. I think because it's such a big part of our lives, it's the reason, or it's how we walk around and how we don't float off into space and, all that kind of stuff. It's such a big part of our lives that we think it's a huge force. It's actually not. It's quite a small force. So gravitational force only becomes obvious when at least one of the masses involved in the attraction is huge. And by huge, I mean planet-sized. So, according to this formula, gravitational force depends on there being two masses and there being a distance between those two masses, right? Which means there's a gravitational force of attraction between all of you. So you all have mass and you're sitting, whatever, hopefully 2 meters apart. So there's a force of attraction between you, but you don't go around all day stuck to each other. You don't spend every time you pass a student outside, you don't end up, that the force of gravity draws you together and you're stuck together walking through the school. And the reason is because there are bigger forces at play. And because gravity will only be noticeable when one of the bodies is incredibly large. And humans are, I don't know, 50, 60, 70, 80, 90 kilos. It's just not large enough for you to feel the force of attraction. So there is a force of attraction there between, like, you guys, as in each other, between you and the building, between you and the cars that are in the car park. Everything that has mass has a force of attraction between them. But the force of attraction is so small that it's not felt unless one of the masses is incredibly large. And like I said, I mean planet-sized large. So the reason we feel the force of attraction between us and the Earth is because the Earth is huge. And the force of, sorry, not the force of attraction, the force of gravity. The force of gravity is what keeps our solar system kind of moving as it does. So, the way our solar system has, like, the sun in the center and Mercury is revolving around that. And then you kind of count out all the planets and they're all moving in their own orbits around the sun. The reason for that setup is the force of gravity. Which means obviously those planets and the sun feel the force of gravity, but of course they do because they're huge. So when you have huge bodies like that, the force of gravity is a really obvious and noticeable force. But if the two bodies involved are small, it's not a very noticeable force. Okay, so that's quite an important concept. So hopefully you get that. And like, if you don't, scribble some notes there, scribble some questions for me and I'll answer them. Like, so just as you're listening to me, if there is anything, just scribble the questions down and I'll answer them when we're back in. This, I don't know, just do it up here. Yeah, see just above there, this formula starts as a proportionality and then you introduce a constant g so that you can introduce an equals and make it an equation. So the bottom line of this, essentially, if we just focus on the bottom line, what it says is that force is inversely proportional to the distance squared. So force is inversely proportional to the distance squared. So because the force on the left-hand side is a numerator, don't freeze on me now. Sorry, just let me shut this down for a sec. It's getting stuck. Because the force on the left-hand side of that equation is a numerator, so I could put it over 1. And the distance squared on the right-hand side is a denominator. It's on the bottom. Then you have an inverse proportionality. So we have done inverse proportionalities twice now, I think. We did it in Boyle's law, and then I can't remember where else we did it. Oh no, it didn't work. Oh, there you go. Okay, so yeah, like I said, because the force is on the top line, the force here, I could put it over 1. That doesn't look like anything. There you go. I could put it over 1. So it's above the line, it's a numerator, and the distance squared is a denominator. That means you have an inversely proportional relationship. An inversely proportional relationship is where one doubles the other halves. Yeah? So we did talk about that relationship before. Now, this is not a straight inversely proportional relationship. It's called an inverse square relationship. Okay, when we did Boyle's law, it was pressure was inversely proportional to the volume. Nothing was squared. Whereas here, we have that force is inversely proportional to the distance squared. So what that means is, if you double the distance, okay, so if I made the distance 2, right, so I brought it from 1 to 2, I doubled it. Because the distance would be 2, and then you'd be squaring it, what would actually happen to the force it would decrease by 4, by a factor of 4, okay, because that 1 over d squared would become 1 over 2 squared, which is 1 over 4, so it would go down by 4. If you look at it again and say, if you triple the distance, okay, so make this a 3. Yeah, because it has to be squared, this would become 1 over 9. So the force has gone down by a factor of 9. So my dog snoring. So you do still have the, when one increases, the other decreases. So here we're making the distance bigger, and that's causing the force to get smaller. So we do have that inverse proportional relationship, but the square changes things. So rather than one doubling and the other halving, if you double 1, the other actually goes down by 4 because it's 2 squared. If you triple the distance, that's 3 squared, so the force is going to go down by 9. If you multiplied the distance by 4, then the force would go down by 4 squared, which is 16. Yeah? So that's an inverse square relationship, which is very important. Um, so hopefully from that it makes sense that the closer things are together, the stronger the gravitational force between them. So as you go further and further apart, the force of gravity decreases quite significantly, actually, because of that square. The force goes down quite rapidly. Um, I actually skipped over it because I shouldn't assume. The gravitational force is always attractive. We will do a very, very similar formula as we go through this. It's also an inverse square relationship formula, and it's not only attractive, it's repulsive too, because it's to do with electric charges. So the force of gravity is never repulsive. It is always an attractive force where the two masses involved are being drawn towards each other. Okay, so I think that's everything there. Right, so you were to do problem 10, so let's have a little look at this. So find the gravitational force of attraction between two steel spheres, each of mass 80 kilograms, if the distance between their centers is 0.5 meters. Okay, so I suppose the first thing is, for the gravitational force between two 80 kilo spheres, neither of them are very big. 80 kilo is, you know, that's quite a normal weight for a man, I think. I think the average weight for a man is about 85 kilos. So that's about the weight of two human men. So based on what I said before, the gravitational pull between these two should be quite a small number. Okay, so let's try it. So we have F equals G m1 m2 over d squared. So F equals, G is given there. Big G is 6.7 by 10 to the minus 11. The first mass is 80 kilos. The second mass is 80 kilos, so we can throw that in. The distance is 0.5 and then square it. Just be careful when you're doing these questions that everything is actually in meters and kilograms, because not so much the kilograms, but the meters, some of the distances are so large, like between planets and things, that they tend to give it in kilometers. So just be careful. So 6.7 by 10 to the minus 11 multiplied by 80 multiplied by 80, and then we're going to divide by 0.5 squared. So I'm just straight into the calculator with all this, and I'm getting 0.1, 2, 3, 4, 5, 1, 7, 1, 5, 2. Okay, so we did expect it to be a really small number. Now, I'm not going to leave it like that. Here's a situation where we should use scientific notation. So I'm going to move it to there. So it's 1.72 by 10 to the 1, 2, 3, 4, 5, 6 minus 6. And it's a force, so it's in newtons. Okay, so that is a really small number, which is kind of to be expected. So again, keep jotting down any questions you have for me. Okay, so here's, find the gravitational attraction between a man of mass 90 kilos and the Earth, where the man is standing on the surface of the Earth. Okay, so we have the Earth, which is a funny shape, and we have the man. Yeah, and the gravitational pull between them, the forces, is the gravitational pull between their centers. So it's from here to, say, here. Do you know what I mean? Now, the distance between the center of the Earth and the Earth's surface is a really big number. The distance from the man's toes up to his belly button is not a really big number. So what we say is that this distance here, when compared with this distance here, is negligible. Okay, and negligible means that it's so small it can be ignored. Okay, and that is an actual scientific term. So the distance from a man's toes to his belly button is like, I don't know, what, maybe 80 or 90 centimeters, something like that. like it's tiny, and the distance from the center of the Earth to the Earth's crust is 6.4 million meters. So it's not going to make any difference in your calculations if you make it, I don't even know how to say it, 6,400,000, I don't know, 0.9. It's not going to make a difference. It's too small to make any difference to that number. So when you do your calculations, adding on the 90 centimeters or not adding on the 90 centimeters isn't going to make a difference. Okay, so we don't calculate it between the center of the two bodies. We basically just assume that the man is so small compared to the Earth that we don't need to take into account the distance from his toes to his belly button. Okay, so that is quite important, because there are times when we have to be super accurate, but there are times when adding something like that in is just confusion for the sake of confusion. It really won't make any difference. It's far too small comparable to the distance from the center of the Earth to the Earth's crust. Okay, so we're going to look at the gravitational attraction between the man and the Earth. This should be a number that's kind of measurable because the Earth is pretty huge. So this shouldn't be a 0.00000 number. So write down the formula. Okay, so G isn't going to change, it's constant, so it's 6.7 by 10 to the minus 11. The first mass, we'll go with the man, so that's 90. Second mass, we'll go with the Earth, which is here. So that's 6 by 10 to the 24. Excuse me. I mean, so that's an idea of just how massive it is. It's 6 with 24 zeros. That many kilos. And then the distance between them, I haven't actually used the word yet, but it is important. The distance between them, because you're going from the center of the Earth to the Earth's crust, it's like going from the center of a circle to the circumference. So it is a radius. Okay, that's important. I'm not sure if you're aware, but certainly in the world of physics, people are aware that the Earth is not perfectly round. It's not a sphere. It's often depicted as a sphere, but it's not. It's actually slightly, it's like if you took like a globe and you put your hand on the North Pole and on the South Pole and just squished it slightly. Now, I've heard people say like it's rugby ball shaped. It's not. It's literally if you took a perfect sphere, put your hand on the North Pole, put your hand on the South Pole and just pushed slightly. That's what it's like. It's sort of flattened slightly top to bottom. So the shape is elliptical. It's not perfectly round, but for the purposes of calculations, we assume it to be round. And that's pretty standard that you make the assumption that it's round, like unless you work in NASA and it's going to make a massive difference because you're trying to get rocket to land or take off or something like that. But for most calculations, it's accepted that it's a sphere. Just wanted to say that. Okay, so the distance between them, oh yeah, it was important that I said it. The distance between them is the radius of the Earth, so that's given up there, which is 6.4 by 10 to the 6, and we're going to square that. So a pretty large distance between them as well. 6.7 by 10 to the minus 11 multiplied by 90 multiplied by 6 by 10 to the 24 divided by 6.4 by 10 to the 6 squared. Okay, so I'm getting a force of 883.3 newtons. Okay, so a much bigger force, which would be expected. Is that okay? Okay, so I actually talked about that already, gravity and the solar system. So yeah, the force of gravity is what keeps the planet in our solar system orbiting the sun. It's almost like the sun has say the Earth on a string, and it holds it and rotates it around itself and rotates it around itself and rotates it around itself, except there is no string. That string is the force of gravity. So every time the Earth is constantly changing direction with regard to the sun because it's traveling in a circle. So a circle is like a constant change of direction. At every instant you're moving in a different direction. If you imagine kind of whirling like a a mass on the end of a string around your head. If you let it go at any point, it would fly off in a straight line. That's kind of what the Earth is like going around the sun. It's like the sun is holding a string with the Earth on the end of it, and it's swinging it around its head. At any point, it would go off in a different direction, but the force of gravity continuously pulls it back in towards the sun, and that happens. That happens for all the planets. It also mentions here the atmosphere. So the reason we can sustain life on Earth, or one of the reasons, is because we have an atmosphere. So we have the air that we breathe, made up of oxygen and nitrogen and carbon dioxide and all that. So the fact that we can support an atmosphere is one of the reasons why we can support life. And our atmosphere is held in place by our gravitational pull. So it's a gravitational force of attraction between the gases in the atmosphere and the Earth itself. So other planets don't have a big enough gravitational pull to hold on to an atmosphere. Quite a few of them, actually. So anyway, that's why we have an atmosphere. So I want you to try a couple of these questions, and we'll move on to gravity and weight tomorrow. There's no experiment to do with gravity and weight, but the calculations are asked all the time. Okay, so these are really important calculations. So please, please, please make sure that you're taking notes as you go through. Anything you want to ask me, like, I definitely won't be in tomorrow, but hopefully we'll be back next Monday. So yeah, if there is anything, just let me know. And the gravitational force of attraction. No, don't care. I think it's 4, 5, 6 I want you to do. So 4 is gravitation attraction between a man of mass. Yeah. Gravitation attraction between the Earth and the Moon. Okay, yeah. So let's try 4, 5, and 6. And then tomorrow we'll do the next bit there, which is gravity and weight. There's a good few calculations on that. And then that's pretty much it. So we're back into turning effect, the last part of this chapter, and there is an experiment on that. So yeah, I will chat to you tomorrow.